Hi, welcome back. It's lesson 1.3b of Foundations of Math 11. It's the unit on proportional thinking, and we're specifically looking at linear scale factor and area and the relationship between them. So we're going to do an exploration on the grid provided. Enlarge the rectangle by a factor of 2. So that means it's going to be twice as big. Okay, so let's do that. Oh, I can do that with my little rectangle drawing tool. So the original one is 3 by 4. So I want one that is going to be 6. 1, 2, 3, 4, 5, 6 by 8. So there's the new one, new rectangle. Okay, and we should color it in as well because this is we are talking about area. So let's color it in. Okay, so the area of the original shape is 3 times 4. Okay, so the area is length times width, which is 3 times 4, which is 12. And it's units squared, or square units. It's 12 of these little squares. Okay, that actually is important. What's the new area? Well, the new area, the area new, is still length times width, but they're different lengths and different widths. It's 6 times 8, which is 48 units squared. What's the scale factor for the area? Well, scale factor, as always, is image over actual. So that's 48 over 12, which is 4. Okay, so our linear scale factor was 2, and our area scale factor is 4. Let's just hold on to that for a minute. Okay, second part, use the graph paper to investigate the relationship between linear scale factor and area scale factor. Enter your results on the table below. So the first entry on this table represents the rectangles that we just did up top. So the original dimensions of the rectangle were 4 by 3. The original area was 12. The linear scale factor was 2. The new shape was 8 by 6. The new area is 48. And then we calculated the area scale factor to get 4. So now we're going to do shape B, which I guess I could label. So this is B. And B is 9 by 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's 6 across. So the original area, 9 by 6, is 54. We're going to apply a scale factor of 1/3. So the new one is going to be 1/3 the size. So it's going to be 2 by 3, like this. Okay. So I'll write it 3 by 2 so that it parallels big one first and then small one. The new area is 6. And the original scale, or the scale factor, is the image over the actual, which is 6 over 54, which reduces to 1 over 9. And I'm going to ask you to pause the video there and go ahead and finish the next two. One is going to be, this is C. You're going to do this by a linear scale factor of 3 over 2. And D, you're going to do a linear scale factor of 2/3 and fill in the rest of the table. Okay? Okay, now let's look at this table. Can we see a relationship between the linear scale factor and the area scale factor? Linear scale factor of 1/3 gets an area scale factor of 1/9. A linear scale factor of 2/3 gets us 9 over 4. Scale factor of 2 over 3 gets us 9 over 4. And a linear scale factor of 2 gets us an area scale factor of 4. So what you see is that the area scale factor is the square of the linear scale factor. Okay, so in fact, We'll write this on the next page. The area scale factor is the linear scale factor squared. And that it's also true that the linear scale factor is the square root of the area scale factor. That's just writing that same thing in the different direction. Okay? And that makes sense because you're multiplying your shape, whatever your shape is, by, like, let's say I'm doubling this, I'm multiplying it by 2 in this direction, and I'm multiplying it by 2 in that direction. So I end up with 4, I have to multiply it by 2 twice. Okay, or if I'm multiplying it by 3, it's 3 in that direction. Oh, good drawing. And 3 in this direction. So now I have 9. And it grows very quickly because you're multiplying it in 2 dimensions. Okay? All right, here's a question for you. You've been asked to create a larger scale copy of this peace sign logo. The copy will be 3 times as large, and you need to determine how many colored squares will be required. What's your plan? Okay, so I totally misled you by putting the graph paper there. You could certainly just draw it, instead of having the one square. I could start. Well, maybe I better start in the middle here. I've got, this is going to be 1, 2, 3. There's one square, and there's a square, and there's a square, and then there's going to be one here. Oh my goodness, that's just so much work. How about if we try it mathematically? Well, I know that the linear scale factor is 3. That means the area scale factor is the linear scale factor squared, which means that it's 3 squared, which means that it's 9. So that's our area scale factor. And since I know that scale equals image over actual, that gives me that image equals actual times the scale. My image is going to be however many squares my original or my actual is times 9. So now I just need to go up and count how many squares were in the original one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So put 21 in here. I need 189 squares of colored paper. Wasn't that easier than drawing the whole thing and counting them all up? I certainly think so. Okay, let's do another example. Thomas has scanned an 8-inch by 10-inch photograph to his computer. He'd like to increase the size, the area, by 44%. This is actually really important. This told you that the scale, that's 44% for area. If you're not told specifically that it's area or volume, which we'll do next, you can always assume that the scale factor given is the linear scale factor, okay? All right, he wants to increase the area by 44%, determine the area scale factor and the linear scale factor. Okay, so the area scale factor, whoops, is going to be 1.44. Okay, that's 144% because he wants to have his original thing is going to be changed to being 144% of what he originally had. So that's where you get that 144%. And then the linear scale factor is always the square root of the area scale factor. So it's the square root of 1.44. So it's 1.2. So the linear scale factor is 1.2. Why are these different? Well, like I talked about before, I'm going to type this out so you can read it. Increasing the linear dimensions increases the area in 2 dimensions. length and width. Therefore, area scale factor is increase in length times the increase in width, which equals the linear scale factor squared. Now, can I actually make that a superscript? Yes, I can. Okay. Okay, so basically one is increasing in a single dimension in a line, and one is increasing in the area. Question C, determine the dimensions of the enlarged photograph. Okay, so the length is 10. We're going to multiply that by 1.2, and that gets us 12 inches. And the width is initially 8 inches, and we're going to multiply that by 1.2 to get 9.6 inches. So there are dimensions, 9.6 by 12 inches. Oops, 9.6 inches by 12 inches. The enlarged photograph will be printed at a digital shop on a color printer. Assuming the white areas will also use ink, calculate the area the printer must cover by the following methods. So if we use the dimensions of the enlargement, area equals length times width. So it's going to be 12 times 9.6, and that's going to be 115.2 inches squared. And if we use the original area and the scale factor, then the area is going to be, or sorry, the area new is going to be the area original times the scale factor, so it's going to be the length times width times the scale factor, and that's the original length and width, which is 10 by 8 times the scale factor of 1.44, and if I put all that in my calculator, ta-da, I get 115.2 inches squared. So it doesn't matter which way you do it, okay? But the purpose of this unit, this section, is for you to do it using the scale factor, okay? Because there's going to be things where there are times when you actually can't do the calculation because you're making an enlargement maybe of something that's unusually shaped. You can't just count the squares of it, okay? Or later on there's questions about volume of chess pieces or things like that. So you can't calculate the new one from the dimensions of the new one. You need to just multiply the volume or the area that you're given initially. Okay, example E, Thomas must also produce a print whose area will be reduced by 25%. Determine the dimensions of the print to the nearest hundredth of an inch. I like to, whenever I'm given something like this, I like to highlight that so that I remember to go back and round. That's where I need to round my answer. Okay, nearest hundredth of an inch. Okay, so the area scale factor, I'm given that. Oh, I'm reducing it by 25%, so my area scale factor is going to be 0.75 because I want to keep 75% of the size. So my linear scale factor is the square root of my area scale factor. So it's the square root of 0.75. And that equals 0.866 and a bunch of other digits. It's really important that you keep all the digits in your calculator. Okay, if you round at this point, your answer will be calculator. Your answer will be incorrect. You must keep them all. Okay, so there are two ways that you can do this calculation. You can have this number in your calculator. So the length equals, or length colon, because we're going to calculate the length here. Image is actual times the scale. So it's 10 because that was our original size for the length, and we're going to multiply it by 0.866 ... You don't need to write all the digits down there, but you do need to keep them in your calculator. and this gets us an answer of 8.66 because that's what it rounds to. You round at the last stage, okay? So there's your inches. The other way you can do this calculation, and I'll just show you a different way for the width. The width is the image is actual times scale again. This time our actual is 8. And this time for our scale, we're actually going to put in square root of 0.75. So you can put that in your calculator and then go times 8 or vice versa. And that gets you an answer of 6.93 inches. Okay? So there's our length and our width of the reduced photo. And there's a difference between reducing by 25% and reducing to 25%. So pay attention to that, right? All right, one more example and then you get to go do some practice. Hannah has made a map of Canada for a school project. The area of Alberta is approximately 661,850 square kilometers. On Hannah's map, the area of Alberta is 264.74 centimeters squared. Don't ask me how she measured that, because that's just silly. Anyway, write the scale of the map in the form of 1 centimeter to x kilometers, where x is rounded to the nearest whole number. So we're looking for a scale that is going to be 1 centimeter to some number of kilometers, okay? Now, this is a scale on a map is always going to be a linear scale, right? So we have to find what the linear scale is going to be. So, but we're not given that. We're given things in areas. So all we can find out is the area scale factor. We have to start with that. So the area scale factor, it's still image over actual. Okay, that never changes. So the image is the map. So the area of Alberta on the map is 264.74 centimeters squared. And the actual size is 661,850 kilometers squared. And we need to include the units this time because the units matter here, right? I can actually reduce that to 1 centimeter squared divided by 2,500 kilometers squared. Now, you're probably looking at that and wondering how in the world are you supposed to know that that can be reduced to such a nice number? Well, the trick would be, first of all, if you're given this question, it's probably going to have some nice numbers in it because we're not trying to trick you. And then what you would do is divide the big number on the bottom here by the smaller number, and you'll get 2,500. So try that whenever you get something that like big, scary, ugly numbers like this, and the smaller ones on the top, reduce it, divide it the other way. Okay, it's worth a try. All right, second step, we need the linear scale factor. So the linear scale factor is the square root of the area scale factor. So it's the square root of 1 centimeter squared over 2,500 kilometers squared. Okay, and if you remember from grade 10 math, that is the square root of 1 centimeter squared divided by the square root of 2,500 kilometers squared. So the square root of 1 is 1, and the square root of centimeters squared is just centimeters, right? If we take 1 centimeter and we square it, we get that, right? And square root of 2,500 is 50, and then this becomes kilometers. So there's our answer. It's 1 centimeter to 50 kilometers. Okay? Part B, on the same map, the area of BC is 376.839 centimeters squared. Determine the actual area of BC to the nearest 100 square kilometers. Okay, I'm going to write scale equals image over actual. And I'm going to use the scale factor. I know what the scale is for this map. We're going to use the area scale because we're just talking about the area of BC. So the area scale is 1 centimeter squared over 2,500 kilometers squared. And so we know that the image of BC is 376.839 centimeters squared. So we can put the x kilometers squared in the denominator, and we can cross multiply to divide to solve that. So x equals 2,500 times 376.839 divided by 1. X equals 942,097.5 kilometers. And we were instructed to do this to the nearest 100 square kilometers, which I forgot to highlight. And so the nearest 100 kilometers would be this 97 rounds up to 1. So this is going to be 942,100 kilometers. Okay? Clear as mud, right? Students find this section really difficult. Just warning you about that. Don't freak out about it. Just grind through the work. Just do the work, okay? Ask for help when you need it, okay? But the biggest thing that you can do is write out this formula. Area scale factor is the linear scale factor squared, and the linear square factor is the square root of the area scale factor. Okay? All right. Go do your practice work and then check your answers, and eventually you'll make your way to the next lesson. Have a good day. Bye.